So we are dealing with the chapter which includes experimental design. Basically, this chapter covers number one as what type of investigation techniques we use during the experiments. And the most important thing that why we are going to learn this chapter is basically why do we use and what do we use as an apparatus during separation techniques and experiments. So what we are going to do, we are going to name appropriate apparatuses for measuring different types of variables. Like if we are measuring temperature, then what type of equipment we are going to use in different types of experiments. Normally to measure temperature, we use thermometer, but obviously there are different types of thermometers as well. There are some type of apparatuses as well that are being used to measure these values of temperature. Then how can we measure pH for any experiment? What apparatus can we use that? Okay, then we are going to identify the techniques to separate and purify different substances. The most important technique that we are going to learn in this chapter, it would be the chromatography. That is the most common use separation technique. Then we are going to discover how melting and boiling points can be used to identify and assess the purity of a substance. This we have already discussed in the previous chapter as well. In the case of water, in which we have discussed the heating and the cooling curve with melting and boiling points and the impurity of the substances as well. Again, the chromatography can be used to separate mixtures of soluble soluble colored substances, and then we are going to state and use the equation to determine the RF value. This RF value is basically related to chromatography technique. We will discuss it what it is. And then the last one, describe how the paper chromatography can be used as a separation to separate mixtures of soluble colorless substances using a locating agent. Basically, to start from the equipments through the separation, the purity of a substance to chromatography. The ultimate achievable goal is to learn what is chromatography and how we can use it as a separation technique, because experimental design is basically related to an investigation. Like you are going to plan it, that you are going to investigate what is there, why is it there, and how you can separate it, and what type of equipment or apparatus is used in this kind of investigation. So there are several steps. There is an organogram related to those steps. The step one is we are going to suggest the hypothesis or an idea to be tested, that what you are going to test or what you are going to investigate, is it worth testing or not? Why worth testing? The reason is that you have to conclude that whether it is going to help with this type of technique or not. Then obviously we are going to draw some information notes, because without the information notes we are not like what variables we are going. Definitely if you want to measure one variable, it is not dependent on, it is actually dependent on multiple other variables or multiple other factors. So you are going to count each and every factor and you are going to note it down, and then obviously you are going to conclude that how you are going to reach at particular stage. That is your ultimate goal. The after the first step, the following step would be what? We are going to draw up a plan for the experiment, and we are going to decide which variables to check and which variables are to keep constant. For example, if you are, let's say, you are going with the to check the relation between volume and temperature, and you are so you are going to obviously keep in that mind that what volume and what temperature you are going to have, and which type of other variables are going to be constant, like pressure is going to remain constant during that setup apparatus. So you are going to check that what variables are you are going to measure and what to keep constant. Then you are going to choose the apparatus that you need. Like let's say you are going to need a beaker. You are going to maybe need a glass rod to stir it to make a solution. So this type of thing, these type of things you are going to need, and obviously you are going to have some operators for that. Sorry, you are going to have the list of those things with you so that you can easily collect it. The consultation part is obvious regarding these two things. Then what we are going to do, we are going to carry out the experiments. Obviously, let's say if you are going to make the crystals, let's say of copper sulfate, you need a burner, you need copper sulfate solution, you are going to heat it for some particular time, and then you are going to give them time to cool it down so that the crystals are made. Once the crystals are made, uh, the experiment is basically complete now. Then obviously you are going to measure the recordings, like till what temperature the copper sulfate solution goes up, and then after that you are going to have the saturated solution of copper sulfate, and you are going to give it time to cool it down. So how much time is given to that solution to make the crystals out of that solution? So these would be the recordings you are going to take, and after that you are going to draw summary of results in tables and graphs, and obviously you are going to make some conclusions. Then you are going to try to decide whether the result supports the original idea or not. Like original idea means, let's say if we are having the experiment regarding the formation of the copper sulfate crystals, then what we are going to do, basically we are going to have an idea that let's say we have some information, let's say from internet or from the book, that at this temperature the copper sulfate is going to be a saturated solution with this amount of copper sulfate solution solute basically. Then let's say for after, let's say for 5 minutes or 10 minutes or 15 minutes, whatever the time is, after this much time the copper sulfate is solution is going to cool itself down and converts itself into the solid crystals. So to verify that idea, you are basically going to that experiment. If you have that information and you are going to test it and you are going to perform experiment on it, after performing the experiment, what you are going to do after performing the experiment, obviously you are going to re-verify that information that you have in the beginning, whether it is true or not, whether the time period that was given in the information, or whether the temperature that was given in the information, is it true or is it wrong. So obviously that idea would, if those recordings or those results they are supporting that idea, that means experiment is over, the experiment is correct, and you are not going to need any further experiment on that. If that information is not true, what we are going to do, obviously we are going to suggest further tests and further ideas to verify, because there are two types of scenarios. One is that the test is correct. The other one is that the test goes wrong. When the test goes wrong, further two options are there. Number one is that either we are going to perform further tests, or the second option is that you cannot perform further tests. The that the sufficient information was there, and this is not going to happen in any way. Normally this the last option does not happen. It's normal, because if something is not happening, obviously we are performing further tests, or we are having different approach, because the research or the search is unstoppable. It does not stop anywhere. So if it's not happening, obviously we are going to perform further tests. So the next comes the choice of operators. But the choice of operators, obviously, it requires proper reasoning, that what do we need and why do we need it. And obviously, we are going to have an understanding of the accuracy level. For example, let's say if you are measuring the temperature, let's say for a liquid, because if you are heating, or like if you are boiling the liquid and you are going to measure the temperature, you are not supposed to use a simple thermostat that which have a maximum level of accuracy, let's say up to 103 Fahrenheit, like or maybe you can say the 37 degrees Celsius, or let's say 45, 44 degrees Celsius even. If the maximum reading that the thermostat can have is, let's say, 44 or 45 degrees Celsius, then how can we use that simple thermostat to measure the boiling point of water? Because the boiling, once you put that thermostat into the water, into the boiling water, what would happen? Obviously, after some time, it shows the reading of 44 degrees Celsius or 45 degrees Celsius, the maximum reading. But the water is still boiling up. If the water is still boiling up, then what is happening? It means you are not, let's say the temperature is 50 or 55, but that last reading is continuously being shown there, or maybe after some time that temperature of water, if you are putting that thermostat into the water, what would happen? Maybe the thermometer would explode. It is possible, because the capacity of the thermometer or the accuracy of the thermometer is finished. So what his point is, you are going to have the proper apparatus as per the requirement. Like if you are measuring the boiling point of water, then it must have at least 10 or 20 degrees above the boiling point of water. The accuracy 10 to 20 degrees above the boiling point of water, so that if the temperature goes up or goes above the 100 degrees Celsius, it should be able to measure that temperature, like how much it has crossed. So this is basically the operator selection, which is quite important due to these things. Then at the design stage, obviously, we are going to plan which equipment to use and write a method of detailing that how to use it. Because if we are not aligning, or if we are not checking that how we can use this apparatus, or we use this equipment, obviously there would be of no use. There would be of no use of selection of operators if you are not able to use it, or if you are not able to handle that apparatus. Okay.
Okay.
Now let's have a video over this.
Going to teach as well. So we have to teach today. Are used. Then comes the SI units. SI units, they are with
Yeah.
reaction through two ways, and also we will get to know how to collect gases based on their atomic weights or molecular masses. So first of all, how do we measure time? We obviously use clock in our daily life, and that's how we measure time in the lab as well. We have two different type of watches. There is something called
Sir, I can't see the video.
a stop.
Sorry.
I can't see the video.
Why you can't see the video?
I can just see the page of the book.
Okay, wait.
Stopwatch, which is digital, as you can see, as a digital dial, and then there's something called a stop clock. There's a difference between these two. Stop clock is analog and stopwatch is digital. Moving to measuring temperature. During this time, we must be resort to this apparatus for quite a number of times. So the first apparatus is called a thermometer. There are various types of thermometer. There is mercury thermometer, alcohol thermometer, but you don't need to know that. Just know that we use thermometers to measure temperature. And this funny looking thing is called that's what we use in industries. Because obviously we cannot. There are like thousands of places where you need to measure temperatures. You cannot go every of those places and then take the thermometer into that place and measure the temperature. We just install sensors and they automatically transmit the information to computers installed in the rooms of the operators. Anyway, moving on, there are different ways of measuring volume. This is the part that is tested in the exams. The first apparatus that you must be familiar with is called a conical flask. It's called conical flask. It's also known as the Merlin Meyer flask. Merlin Meyer flask. Okay. As you can see, the numbering SS is visible 500, 600, 700. This is not that accurate because if, for example, if you want to measure 520 centimeter cube, you won't be able to measure volume of 520 centimeter cube in this apparatus that is conical flask. Then there is something called graduated cylinder. It is more accurate as compared to conical flask. By the looks of it, if you see, there's 30 to 50. There are like 30. There's 32, 34, 36. But again, if you want to measure 30.1. You won't be able to measure it with the help of a graduated cylinder. So it's not extremely accurate. It will do a lot of jobs, but obviously if you want to measure volumes that have decimal points, obviously you cannot do that. Similar is the case with the beaker. This is 10, 20, 30 and 40 ml. So if you want to measure 15, you won't be able to. You cannot get it exactly right. You can have a vague idea about it, but even you can get a vague idea about 15, but what about 14 or 13? You won't. So these are not very accurate. Obviously, we use these apparatuses for the volumes that are marked over here, but other than that, we don't use these apparatuses. The most accurate apparatus for measuring volume is called a burette. It's called a burette. As you can see, between each unit, 45 and 46, there are 10 markers. So obviously you can measure 45.1. And similarly, you can measure 47.3 or and 48.9 or anything, in decimal points. So it can measure up to 0.1 marker. So burette is the most accurate apparatus that you need to study in O-levels. And then there's something called a pipette. This is not exactly an apparatus to measure volume. It is mostly used to transfer a particular amount of volume from one piece of apparatus to another piece of apparatus. For example, if you want to transfer some liquid from a conical flask to a beaker, maybe, let's say 10 centimeter cube, if you want to extract from this conical flask, you will use a pipette whose capacity is 10 centimeter cube. And then you press the suction bulb, liquid gets sucked here, liquid gets sucked in, and then when you release this suction bulb, liquid stays inside pipette, and then you can simply press the suction bulb again, and then this liquid is, that's how it works. Again, many students get confused between burette and pipette. Just make sure there is a telltale sign of a burette. You'll always see a tab at the end of a burette. This tab is open and then this liquid starts falling down. The application of burette we're going to study in asynchronous basis, so stay tuned for that video as well. Okay, so how do we measure rate of reaction? Rate of reaction, how do we define it? The rate means time. Whenever there is a mention of rate, we're basically talking about time. And we are measuring rate of reaction, which means we are monitoring reaction with respect to time, or we can say we are measuring speed of reaction. A speed of reaction can be measured by two ways. One of the ways is mentioned on the slide, that is by collecting the volume of gas. For example, this is a conical flask. I put the reactants over here. This is a reaction in which a gas is released. This gas will enter the delivery tube and will enter the gas syringe. There is a plunger in the gas syringe. As the gas enters the gas syringe, it starts to push the plunger back. It keeps on pushing the plunger until it is releasing. There comes a time that this plunger stops moving. It means that no more gas is actually entering the gas syringe. At that time, we know that the rate of reaction is complete, and since you can see there are markings over here, let's say this is like 10, 20, 30, 40, 60. Whenever the plunger stops, that would be the marking for the volume of the gas release. So that's how you measure the volume of gas. And while all of this is happening, take a stopwatch and you get it running. So you basically measure the volume of gas that is collected over time, over a certain amount of time. And what would be your what would you sign when you are going to stop the stopwatch? It's when this plunger stops moving, because this is a sign that gas is not further released. So there's another way of measuring rate of reaction. In this method, we are not going to collect the gas. Instead, we are going to let the gas go into the environment. We don't need the gas. But what we are going to do is, we are going to place the conical flask on a mass balance, an electronic balance. Now, when the reaction starts and the gas starts releasing, there will be a fall in this reading. Over time, as more and more gas is being released, there is going to be a decrease in this mass. There comes a time that this mass is not going to be decreased any further. For example, at the start of your reaction, when you started the stopwatch, the mass was 246.32. Let's say after 1 minute, it decreased to 245. After 2 minutes, it decreased to 243. After 3 minutes, it remained at 243. After 4 minutes, it remained at 243. What does this mean? These constant values means no more gas is being released because there is no loss of mass. It makes us realize that the reaction is complete. Then you will stop the stopwatch and you will write down the loss in mass, which would be your initial value minus final value of mass, and you will divide it by the time at which it is loss in mass is recorded. So that's all from rate of reaction. Now we are going to understand how do we collect gases. For example, if you have a gas and you need to collect that gas, there are certain properties that you're going to consider. First, you'll have to see whether the gas is soluble in water or insoluble in water. You will have that information while solving these questions, whether a gas is soluble in water or insoluble in water. If the gas is insoluble in water, then it will be collected over water. If the gas is insoluble in water, it will be collected over water. Simple. This is a reaction mixture in which a gas is released. It will go into this delivery tube and bubble into water. Since it is insoluble in water, it will be collected over water. Here. Remember, this apparatus is only used for gases which are insoluble in water, because if this apparatus was used for gases which are soluble in water, gas wouldn't have been able to collect over here. Gas would have entered the water and would have stayed here because it is soluble. So this apparatus is only used for gases which are insoluble in water. And if the gas is soluble in water, then you'll have to check other properties. If it is soluble in water, then you'll have to see whether it is heavier than air or lighter than air. If it is heavier than air, then obviously it is going to travel downwards. And as it travels downwards, we collect it. So this method, which is quite commonsensical, is called downward delivery method. Downward delivery method. Since the gas is heavier than air, the mass of air is 29 grams. If it is heavier than air, it's going to travel downward, then that's how we collect. It's called downward delivery, or it's also known as upward displacement. What does that mean? Upward displacement means when the gas is entering air, obviously this empty container or collection flask, this will have some air in it. Okay, when the gas enters here, obviously the air inside it will make room for the gas, so it will go up. So this upward displacement comes from this phenomena. This name comes from this phenomena, but you don't need to remember this. Just know, okay, this is downward delivery method. If the gas is heavier than air, it will be collected by downward delivery. If the gas is lighter than air, then it will be collected by upward delivery. It's not upward displacement, it's upward. It's not downward displacement, it's downward. At lighter than air, it is travel upward, it will be collected by upward delivery. So that's all from the first chapter. Hopefully you have understood this one. Let me give you a quick recap. We learned how to measure time, and that is through stopwatches and stop clocks. Then we learned how to measure temperature, that is via the thermometer and sensors. Then we understood various apparatuses that is used to measure volume. There is a conical flask, there is a measuring cylinder, there is a beaker, and then the most accurate one is called a burette. Then we learned how to measure rate of reaction by two ways. One is by collecting the gas and dividing it over the time in which it is collected, and the other one is by measuring the loss in mass and dividing it by time. As far as gases collection are concerned, if you have a gas that needs to be collected, first property that you'll have to consider is whether it is soluble in water or insoluble in water. If it is insoluble in water, then you are going to collect it over water. If it is soluble in water, then you'll have to see whether the gas is lighter than air or heavier than air. If it is heavier than air, then it is going to be collected by downward delivery. If it is lighter than air, it is going to be collected by upward delivery, as shown on your slide.
Yes, Maya.